All right, welcome everybody to the 27th and final lecture of Introduction to Spacecraft Navigation. I promised myself I wouldn't get emotional for this lecture, but I don't know, we'll see if I can keep that promise. We're going to be discussing crater-based navigation, which is a subset of terrain relative navigation. So let me go ahead and share my screen, and I want to bring us back, not to this, but to this, to the course map. So we like to refer back to this course map whenever we start a new unit. It's always good to review. So we talked about orbital mechanics for several lectures. We talked about estimation theory for several lectures, triangulation and trilateration. We had a section on inertial navigation. We had a four lecture unit on how star trackers worked, and you put together your own star tracker for homework 3. Homework 4, or sorry, homework 4 was the star tracker. Homework 5 was writing your own Kalman filter. That's the algorithm that runs on the flight computer. And then homework 6 was horizon-based optical navigation using an image of Pluto to get your relative position in the camera frame. And what we're going to be talking about today is another form of optical navigation. So we're still on this green image, but it's going to be a little bit different. So you might remember from our initial discussion of optical navigation, here are 3 images of the moon, or in this case, the Earth and the moon. And we talked about how if the two bodies are completely unresolved, you just see 2 dots in the image. You can centroid both of those dots. You can get a line of sight direction to each of them, and you can estimate your position by triangulation, right? You've got a line of sight direction to the Earth, a line of sight direction to the moon. 2 lines in space intersect at a point, unless there's some noise or error or something else going on. So there's your position in space. If you have a resolved image of the moon or the Earth or Pluto or what have you, then what you can do is find limb points, fit a ellipse to those limb points, and ultimately solve for the observer position using some fancy factorization methods. And that was our kind of 2-lecture unit on horizon-based optical navigation, which is sometimes abbreviated as just OpNav. Some people use OpNav to mean this specifically. Some people use OpNav to mean any navigation with cameras. So you need to be careful, to ask people to define OpNav when they use it. And then the third example, which we kind of introduced and then didn't come back to, is what we're going to come back to today, which is terrain relative navigation, or TRN, which is also a broad umbrella term. There's many, many types of TRN. What we're going to focus on today is one specific problem, which is actually illustrated here, but I'm going to do my best to kind of copy over that illustration. And so the question looks like this. Let's say you've got an image, and we're specifically talking about Earth's moon today, but it could be a different celestial body, could be Mars, and that's fine too. And let's say that your image looks like this. So that's the curvature of the moon. This is space. And then you've got big old crater, smaller crater, 2 craters over here, huge crater, maybe another crater right there. And I say you can navigate using this image. Now let's sharpen the pencil on that. When I say navigate, I mean 2 things. I mean position, spacecraft position with respect to the moon, and attitude. Okay. So my open question, so anybody who's feeling brave can key in their microphone and talk about this. How do we do that? How do you navigate using this particular image? What are our options?
I'll try to answer. So,
Sure.
like in that one extra credit on that one homework where they knew the names and locations of all of the craters on the moon, I think it was. So
Yep.
then you could use like the centroids and sizes of all the craters and their distances relative to each other to try and find which craters they are and kind of do like an image based navigation like we did for stars, but this time it's for craters.
Italia, I am so proud of you right now. You are a real spacecraft navigator. Like you
Nice.
could have read off my notes and that would have been exactly it. So yep, no, that you nailed it. That's perfect. So and everybody else who was thinking the same thing but just didn't say it, you're also a real spacecraft navigator. So the idea is we're going to identify craters in the image And then we're going to use some of the techniques that we already know. Actually, it's going to be a little bit of a deviation from what we already know. But the idea here is detect and identify craters. We're going to talk about how that's done. And then solve for pose. And pose is position and attitude, right? So if you know your position with respect to the moon and your attitude in the moon-centered, moon-fixed frame, both of those together is pose. So that's just a nice abbreviation that we have. So a couple of notes for you. The first part of this lecture is going to be a little bit wordy. We're going to hand wave over some of the procedure, but then we're going to land on a big fat math problem, and then we're going to spend some time on that math problem. So first the words, then the math. So navigating relative to features on the surface of a planet. Relative to features on the surface of a, we'll say planet or moon or asteroid, because this also works on asteroids, is called terrain relative navigation. Or TRN. I should make a note. That's supposed to be a star. There we are. This is an area of active research. Now, that's not to say that the other things we've learned about in this class are not still areas of active research. There are still people that are coming up with new solutions to problems in estimation theory. There are still people that are working on methods of orbit determination and other problems of orbital mechanics. There are still people that are trying to kind of, squeeze more juice out of the lemon when it comes to star trackers, or, there's a ton of, like, Kalman filters are absolutely an area of active research. But I want to make it clear that specifically TRN is pretty cutting edge stuff. Like the idea of navigating relative to surface features on the moon, or some sort of automated crater detection, or some method of, building a shape model or structure from motion or stuff like that. Those are definitely problems of the last 20 years, and we're on to contemporary problems. So it's kind of like when you're working through math class and you're in, middle school or high school, all the names are like ancient Greeks. And then when you're a little bit older, it's like, oh, now we're learning about mathematicians from the 1700s. Like you're slowly catching up with history as you go through school. And then eventually, by the time you're in college or graduate school, you're all caught up. Well, if you're learning about TRN, you're basically caught up. Like this is kind of where the field is right now. And this is something that people are still working on. Not to say that the other areas aren't still being worked on. So one idea is terrain features can be identified and that allows us to get what's called a global pose. So in plain English, this would be something like, I know my latitude and longitude because I know the name of that crater. So when I think of global pose, we're thinking of latitude, longitude, in some global reference frame. Or unidentified terrain features, which don't need to be identified, can be tracked. Unidentified terrain features can be tracked while they're still visible. So the plain English form of this would be, that rock moved X pixels since my last image. But rocks don't move. least ostensibly, rocks don't move, unless you've seen the documentary Apollo 18 about the moon spiders. That's a joke. Rocks don't move, which really means, so really, I must have moved y meters. That's the idea. So this is kind of a local relative navigation. This would be something like, I'm tracking these rocks in an image, and then my rover creeps forward what I think is 2 meters, and then I assess how much the rocks move, and I realize that actually I moved 1.8 meters, and my wheels must have slipped for a little bit. Oh, let me go check my wheel cameras. Oh yes, look, we can see that this one tire track shows that we didn't move as much as we thought we had, right? So there's different forms of TRN. So this second method here is a little bit closer to what you might call visual odometry, whereas this first feature is more of like a global pose estimation. So today, that's meant to be an O. Wow, 1 week of not giving lectures and my handwriting drops off precipitously. I apologize. Today we will discuss crater-based navigation in the context of lunar exploration. I guess we could probably extend this to Mars. So we'll say lunar/Martian exploration. So here's the neat part, and Italia was right on the money when she said this before. If you squint, crater-based navigation looks like star trackers. Crater-based navigation looks like the procedure for star trackers. What do I mean by that? Well, there's 4 steps. So we'll do some dotted lines here. Okay. The first one is if you've got an image of the moon. Let's say you're looking straight down at the moon and you see crater, 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 big crater, small crater. Then the first step could be, oh, I recognize this crater, I recognize this crater, I recognize this crater, and using some method, which we have not discussed yet, I'm going to identify craters. So we'll start with this. We'll start with crater detection in an image. And I've kind of already alluded to, we're also going to compute what we might call invariance based on those craters. So the same idea as with stars, except it's going to be a different invariant. Then let's say this is the whole moon and you've got some big craters and some smaller craters. I just want to make it clear that this is the moon. This is not like a chocolate chip cookie. Then someone somewhere at some point has probably, and this is actually true, made a crater database. So crater database generation, which sounds a little bit like our star databases, right? Or our star catalogs, which we learned about all the way back in lecture, oh, was that 19? And then there's going to be some index search, some kind of database search, where you've got, we'll call it invariant 1, invariant 2, invariant 3, and you've got a bunch of points in your catalog. And let's say that we're looking for all of the points which are in this field, and hey, look, there is one. And so you've got, okay, well, within this region of 3D space, we're going to return all of the craters, or all of the, craters or groups of craters which meet that definition of our invariance. So there's going to be some, say, invariant based crater ID. And then the fourth step, if this is the moon and this is your spacecraft, and you're looking down at these three craters, wow, those lines are supposed to line up a little bit better. Let me try one more time. There we go. Crater here. Let's start with the craters and then go to the spacecraft. That's better. Finally, you've got relative pose estimation, which is known as the perspective endpoint problem, or PNP. That's where we're going to be spending the bulk of our time today. But you'll notice that if we go back to lecture 18, when we first learned about star trackers, looks mighty similar. Maybe my ability to draw things has gotten a little bit worse. Maybe it's gotten a little bit better. But first, we've got image processing to find stars. Then we've got building a map of all the stars in the Milky Way or all of the nearby stars that are worth using to navigate. Then we've got some sort of a database search, which I'm sure was everybody's favorite part of homework 4. And then we've got Waba's problem, which is solving the attitude of the spacecraft. Here, we've got image processing to find craters. We've got some sort of crater database generation. We've got invariant-based crater identification, and then relative pose estimation, which the PNP problem is actually the cooler older brother of Waba's problem, because PNP allows you to solve for your position and attitude simultaneously, whereas Waba's is just attitude. And so we will spend most of our time today on the fourth part, but I'm at least going to nod to the other three. And I should make a point here. One of the best papers on this topic, you want to learn all about it, have to give a shout out to my former mentor. I am biased. Is called Lunar Crater Identification in Digital Images. By Christian Dirksen and Watkins. And this was published in 2021. And I guess I should say Anne McKee, because I'm mentioned in the acknowledgments of that paper. So there's me tooting my own horn. I had something to do with it, but I'm not one of the top 3 authors or any of the authors on the paper. But this is research that came out of RPI. And this is, definitely contemporary work. In this case, it's 3 years old, less than 3 years old, because this would have been around the fall of 2021, I believe. I could be wrong about that. I might have my wires crossed, but very, very recent work. So if you want to learn more about crater-based navigation, this is the paper to start with. Parts of it can be a little bit dense. It references hundreds of other papers that are good to kind of get your toehold on how this whole method works. But I would be remiss if I didn't let you know that that's a good paper. So any questions before we switch to discussing crater detection? All right. So how do you detect a crater? Detecting craters in images is more of an art than a science. There are many, capital, all caps, many published methods using both classical image processing techniques as well as machine learning and neural nets. And again, this is an area of active research. So classical methods often leverage some a priori, which means before the fact, state knowledge So for example, like sun direction. So for example, I'll draw a little doodle over here and then I'll fill in the words over here. But imagine this is your image, right? Now, I've read a handful of papers on non-machine learning crater identification techniques, and this was the understanding that I came away with, but I'm sure that somebody could correct me if they'd read more than I had. The general understanding that I have is if you know ahead of the game that the sun is over here, then what you can do is start scanning along the image along the period of sun direction. And what you're going to find is, and we're just going to focus on an image of a single crater, but you can imagine there being more craters in the image. Every crater, if you actually look at a picture of the moon, is going to have some region which is darker than the rest of the image, and then some other region which is brighter than the rest of the image. And so you figure the bright region is going to be opposite the sun. That's like the rim that the sun is hitting. And then the dark region is going to be on the side that's towards the sun. That's the shadow. And if you take the outside of the dark region and the outside of the bright region and kind of fit an ellipse to it, you've got, well, pretend I did a better job fitting that ellipse, but there's your crater. That's basically the idea. So there's find dark regions in the image, find bright regions in the image, correlate them with one another because they should basically be aligned with the sun scanline direction and roughly the same size. So let's say there was another crater over here with a dark region and a bright region, and you would not correlate this dark region with this bright region because their sizes are so different and they aren't perfectly aligned, that sort of thing. But this would allow you to find a second crater in the image. It's going to be something like that. Sure, there's other methods, but this gives you kind of a flavor of one way we could do it. So to put that in English, each crater has a darker region and a brighter region. And we'll call these equal and opposite. Correlate regions along the sun direction. And then fit an ellipse to region pairs. So that's kind of one way of solving this sort of problem. Machine learning methods typically involve a neural network. So I am skeptical of machine learning and neural networks in spacecraft navigation. I think that it's a very promising new field of study, relative new field of study. I feel like nowadays the literature is saturated with people throwing machine learning at already solved problems to see a very small increase in the performance of the solution. Sometimes it's just a hype train. Other times you've got problems that genuinely are really well suited to neural networks. And I think that neural networks can solve the crater identification problem pretty well, asterisk. Like it's definitely a problem that feels like a neural network problem, right? The same way that like handwriting analysis is a neural network problem. Like this feels like a neural network problem. It's not without its problems and kinks, but you know, I definitely think that it's worth looking into neural networks for crater identification. And so in this case, I'll draw a quick little doodle over here. But so the general procedure is something like train on myriad sample images and then Well, I mean, that's basically it. So you've got a whole bunch of images of craters. And let's say you've got a picture of the moon that looks like this, and you got some bigger craters and some smaller craters. And then what you do is you train a neural net to go, yep, that's a crater, that's a crater, that's a crater. Maybe it finds this one. Maybe it misses this one and it finds a complete dud. So you're going to get some false positives and false negatives. The problem is coming up with training images is hard. Right? You might say, oh, why don't we just use some of the billions and billions of images of the moon that we've taken? It's like, well, actually, there aren't that many images of the moon, which is a bit like, hear me out. That sounds crazy, right? Uh, the Apollo images are great. There are many of them. There are many thousands of images that Apollo took. However, their correlation with truth data of the spacecraft position and attitude when they were taken, which you kind of need for this to work, is iffy. Um, you might say, well, don't we have like a whole map of the moon, like Google Moon, the way we have Google Earth? It's like, yes, that was made using the Lunar Reconnaissance Orbiter. What was that? The LRO camera, LROC, which is a push broom camera. So it doesn't really take pictures. It kind of just scans the whole moon so that later you can produce a composite image. But what we really need, if we want to make this method work, are thousands and thousands and thousands of images of the moon where we know exactly where the spacecraft was when it took that image. And that's actually pretty tricky to come by. Or you could just render the images using some sort of image rendering software, but then now you need to create a fake image of the moon, which is good enough to trick a neural net. And despite what some flat earthers would have you believe, it's actually really hard to fake pictures of space convincingly. It's actually, some would argue it's easier just to send a spacecraft to the moon than it is to try to fake an image of the moon. But it's definitely a problem. So I'll just comment on that briefly. So the neural network will draw a bounding box around craters and attempt to find rim points. No promises. The bounding boxes are generally pretty good. The rim points are hit or miss, in my experience, working with algorithms like this. Now, your mileage may vary, right? Now, quick note on homework 7, those of you that are doing homework 7, maybe I'll use blue for my homework 7 notes. On homework 7, just find approximate centroids of your favorite, we'll say 4 or more craters by eye. You can open them up in Microsoft Paint, or you could do like IM show in MATLAB, and you can kind of go, yeah, I think that's about the center. And you'll get pixel coordinates for those, right? That's the idea. Okay, questions on crater ID. Otherwise, we're going to talk about crater databases. And we're going to keep charging until we hit that math problem, and then we'll take a break. All right, feel free to interrupt me with a question if you have one. So, scientists have already created databases of lunar and Martian craters. Isn't that nice? Oh, hang on. Created. And this is kind of similar to a star catalog. So we are going to be borrowing data from a different field of study because it's useful to us as navigators. These often contain, among other things, location, so latitude, longitude of crater center, diameter, and ellipticity, how much it is not a circle. It's actually a very fascinating discussion point. The vast majority of lunar craters are circles, but impact angles are very rarely normal to the surface of the moon. And we can talk a little bit about why that is, but it's like an interesting physics problem of like, well, why is it always circle? Shouldn't it be that if a crater hits the moon at a glancing angle, that it kind of leaves like a smeared out crater that's like a, you know, like a gunshot ricochet kind of shape? It's like, nope, that's actually not how that works. So overwhelmingly, lunar craters are circles or very close to circles, right? Because nothing's ever truly a circle, but you could look at the eccentricity. Now, in much the same way that there are, for all practical purposes, an infinite number of stars in the sky, but we really only need the bright ones to navigate, it's the same deal here, right? There's probably a finite number of craters on the moon. If you had, you know, if you were infinitely long-lived and you were bored and you wanted to go to the moon and count all of them, you could do it. It's probably a countably, you know, large number, but for engineering purposes, there are infinitely many craters on the moon. There are, for all practical purposes, infinitely many craters on the moon and Mars. Just like there are an infinite number of stars. But we can create we're going to call them mostly complete global databases of large craters. So the moon is kind of a fractal pattern, right? If you zoom in on a surface of the moon, it's just more and more and more smaller and smaller and smaller craters. But if we say, oh, find me all of the craters bigger than 1 kilometer in diameter, that's actually something we can work with. That's going to be a very large number, but it's not infinitely many craters, right? We can work with that. So one example, and it's the one that I'm going to focus on, is what's called the Robbins Crater Database. And actually, there are not one, but two Robbins Crater databases, one for the moon and one for Mars. The Robbins Crater Database has more than 2 million entries, large but finite number. Includes almost all lunar craters with diameter greater than 1 to 2 kilometers. And I should say this is plenty for navigators. We don't need to identify every crater in the image. We need to identify enough craters in the image. How do you know when you have enough? We'll talk about that one thing at a time. Now, on homework 7, we're not going to do Robbins Crater Database detection. We're just going to manually identify craters using the website that I provided, which is quickmap.lroc, which is Lunar Reconnaissance Orbiter Camera, Arizona State University.edu. And I just found a mistake in my notes, so bear with me for a second. So this is a little bit like Google Moon. There literally is something called Google Moon if you look it up. It's Google Earth, but with the moon. We need something that's a little bit higher resolution than that. So if you go on QuickMap, LROC, ASU.edu, and you go look for, the moon, and you can kind of scroll around like a globe, and you can mouse over specific regions of the moon, and it will tell you the latitude, longitude of those. So if you take the time to identify a certain crater and you zoom in and go, oh, this crater in the image is this crater on the moon, blah, 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 blah. what you'll end up with is a list of latitude, longitude coordinates to craters in the image, which is what we're after for homework 7. So questions on crater databases, Robin's crater database, or are we good to go for a little bit? All right. Thank you for bearing with me. One more short topic, and then we'll take a break. Y'all have been very patient. Next is invariant-based crater ID. We're going to try a little harder to underline that properly. Just bear with me here. Go. So we can use techniques from invariant theory to determine the number of invariants for a set of D craters. And I want to make a note, this is much easier said than done. Invariant theory gets pretty spicy, and some of the more opaque parts of the paper that I pointed you to deal with actually mathematically proving that, very rigorously proving that for the geometry problem that we have, there are exactly this many invariant qualities. And that's no small feat. So I'm going to gloss over that at a very high level today, just to give you an introductory understanding. And that's something that you could absolutely look more into if you wanted to. So recall that a set of D stars, remember back to star ID, has 2D minus 3 invariants. So we would use the interstar angles, basically, given unknown observer attitude. Well, if we consider, we're going to go through 3 cases. If we consider a crater is really a 2D ellipse, which we're going to call a conic, in 3-dimensional space. If we consider D conics in 3D space and no other constraints, then there are no invariants. That is the symbol for does not exist. There are no invariants in general, right? If you've got just D circles floating in space and you're looking at them from an arbitrary viewing point, there is nothing about them that is completely invariant. There's no way to say, well, I can recognize those 3 craters based on blank. There's just nothing to work off of. Okay, so let's start adding some constraints. If we consider D conics on the surface of some huge ellipsoid, like the moon, then there are 3D minus 6 invariants. Okay. Now, if we go even further, let's say it's a low altitude image, we're going to approximate the surface of the moon is flat for the purpose of that image. So don't tell your flat earth friends about this, but sometimes you can approximate the surface of a celestial body as flat for a narrow enough field of view camera or a low enough altitude image. So if we treat the moon as being flat, or if we consider D conics on a plane, there are 5D minus 8 invariants. Okay, so that means, say thus, we can leverage invariance or crater ID using high and low altitude images. So you might be saying to yourself, okay, that's great. What are these invariants? Because for the moon, I'm sorry, not for the moon, for stars, we like to use interstar angles. And there are other options. There's also the dihedral angles formed by stars, but it's basically angles. For craters, it's not that simple. It's pretty complicated to compute what the invariants are. They have not really that much in the way of a physical meaning. Like you can't point to a crater and be like, well, that part of it is the invariant. It doesn't really work that way. But if you have the information about the craters and their relative position and attitude from one another, you can compute parameters about them that are invariant, which are difficult to point to, but which nonetheless serve as kind of numerical descriptors or name tags. And that's something that if you want to take a look at the paper I referenced you to, then that is, absolutely something you could look more into. But for now, these invariants, we're going to leave these as arcane, ethereal, just numbers that you compute about craters, and that's going to be enough for our discussion today, because I want to get onto that math problem. So when we try to solve this, a navigator must use a crater database to construct an index of invariance. Sound familiar? For pairs or triads of craters before flight. And this index must be rapidly searchable. Must constrain index size, so can't be too large. And we will focus on craters that the spacecraft is likely to see. Right? So if you know hypothetically that your spacecraft is going into an equatorial orbit of the moon, around the moon's equator, it doesn't make a ton of sense to focus on craters on the moon's north pole, which you're probably never going to see in the image. But you'll notice that this kind of parallels some of our considerations when we were building our interstar angle indexes from before, right? We're talking about, why don't we focus on star pairs that have a narrow enough interstar angle that our camera would actually see it. And we also need to take steps to make sure that our index doesn't get too big, and we need to generate this index in such a way that it is a rapidly searchable database. These are all similar problems. And I should say, and you'll be relieved to hear this, that on homework 7, none of this is necessary. So homework 7 is kind of a baby version of the problem. And I'd say that not to be condescending, because homework 7 is a tricky math problem. But all the trickiness is in the part that we haven't talked about yet, which is the perspective endpoint problem. A lot of the other things we're doing manually. So we're manually identifying craters, manually matching them to craters on the moon, manually getting that as crater latitude, longitude. So on homework 7, none of this is necessary. Okie doke. So the last bit I want to talk about is pose estimation, and it's going to take a minute to work through this math problem. So why don't we take a break? It's 6:55 now. Let's say we'll take a break, and we'll be back at the top of the hour, and then we'll wrap up our math discussion. We might go a little bit longer than we'd like to today. I apologize. I know y'all are busy, but it's not like we can put this off till next lecture, so bear with me. I'm going to try to get through the math as quickly as possible. All right, take a break.
Paul.
Yep, I'm still here.
I wanted to ask because I was looking for a way to check my homework 7 because
Mhm.
like if I get a wrong position with the crater image, I have literally no idea. So I had a picture that I took like on a plane of like Manhattan when I was on the way back from spring break. Would that be like appropriate to test it with? Because like I know the approximate location the picture was taken.
Oh, I'm interested. So are you talking about like identifying features in that image?
Yeah.
And then I guess what would the feature like because I don't have the picture in front of me. Can you see like Manhattan Island and you can see
Yeah,
like
you could see like almost the whole thing. Like I was picking points to be like, oh, I can see like the Statue of Liberty and like the Freedom Tower and like the Brooklyn Bridge and that kind of stuff.
I'm going to say the same thing to you that I said to Italia. I am so proud. That is exactly the right way to be thinking about this as a navigator. You probably knew roughly where you were on the plane when you took that picture. You can go find the lat long values of those points and you can solve the PNP problem and then use that to check your work. Is that something that you've done or is that something that you
Yeah,
plan
that's
to do?
that's something I've been trying to do over the weekend, and
Okay.
it hasn't been working because I guess there's something wrong. But I didn't know if that was because like my position was too close to the plane that the points were on, or it's a picture that's from pretty high up, but
Yeah.
like
You should be able to get away with that. Just the fact that you're doing this on your own image is so cool. Um, so there are different methods of solving the PNP problem, and that's what we're right about to talk about is the PNP problem. Some methods really don't like it when your points are all coplanar. And if you're on an airplane looking down at the Earth, those points are basically coplanar, and it won't like those. But the method that I think that you're working on, which is very similar to the method that I mentioned here, can handle coplanar points just fine. So I don't think that's the problem. I think it's worth going through and double checking. Um, Now, the other thing I'd recommend, are you working in MATLAB or Python for homework 7?
MATLAB.
MATLAB. MATLAB has a built-in perspective endpoint solver that you could use. I assume you coded yours up from scratch, which is what I was hoping you would do. So you
Yeah,
did
I
do it.
was I was trying to use theirs and I couldn't get the camera intrinsic structure to work, so I haven't been able to test that.
Okay,
Cause it
I can
like
work with you on that because that we should be able to get that running. However, the inbuilt MATLAB version of PNP doesn't like coplanar points, which is why I was
mm,
like, oh, you should go write your own. So your mileage may vary with that. But it sounds like you're very close to being done, which is great. So
yeah, I wanted to ask you about it after class. So
great. Yeah, no, bring it on. We'll give everybody one more minute to go to the bathroom or get a drink of water. I might actually refill my water here real quick and then we'll keep talking. All right, we're back. Let's do some math. So, erase this here. All right, so then, on to the fourth topic. So, as a reminder, before break, we talked about crater detection, crater databases, and invariant-based crater ID. We kind of glossed over those. I gave you a quick hand wavy explanation of each of them. We're going to linger on this third one, which is the relative pose estimation. And so, or in this case, I'm going to call it spacecraft pose estimation. So the final step is to compute the relative pose of the spacecraft and the planet. And so we will focus on, I'm getting myself all mixed up. Okay, let's just do this. Final step is computing position and attitude, which as a pair, those are referred to as the pose, of the spacecraft with respect to the moon or Mars, etc. Okay. We will focus on the lat long of crater centroids. Okay. Now, essentially what we have is this problem. Given line of sight directions in the camera frame to points in the world frame, no, I should say known points in the world frame. I'm going to cheat. You can't do this, but I can do this. We're just going to scooch all of this down. Sorry. Maybe I can't do this. There it is. There we go. Given line of sight directions in the camera frame to known points in the world frame, compute the camera pose, position, and attitude. That's the problem that we're left with here. Now, we should say this. If the relative attitude is known, wow, all right, can't spell today. If the relative attitude is known, e.g., you have a star tracker, then this is a triangulation problem. You might be thinking, Paul, haven't we worked so hard to just get back to that problem that you gave us on, what was it, homework 3, problem 2, which is here's the line of sight direction to a bunch of craters, here's the latitude, longitude of all those craters. And it's like, yes, if we knew our attitude, then this would be a triangulation problem. What if we don't know our attitude? So in general, if you're trying to solve for position and attitude at the same time, this is the cooler older brother of Waba's problem or triangulation. It is simultaneous triangulation and Waba's problem, which is referred to as the perspective n point problem, which is abbreviated as PNP. So if you're using 3 points, it's the perspective 3-point problem. If you're using 4 points, it's the perspective 4-point problem. But the general case is the perspective n-point problem, or PNP. And so what that would be is, given n image points and corresponding world points, estimate your observer pose. That's basically what it boils down to, which is exactly what I wrote up here, so I'm not going to write it twice. This is a very well-studied problem. There are many papers on this topic, and there exists, this backwards E means there exists, MATLAB and Python toolkits to do this. What we're going to go over, what follows, is a method that will work for 4 or more coplanar points, such as the crater rim centers on the surface of the moon. This is by no means the best way of solving the problem. This is just the smoothest learning curve, the way I see it. Like, if you needed to explain the PNP problem to somebody in 20 minutes, this is it. And if you look, there are about 20 minutes left in class, and we're going to try to do PNP. So what we're going to talk about is a method that is referred to as Grunert. You know what? I've only read this name, so it could just as easily be Gruner or something really fancy like that. But I'm going to say Grunert P and P. And this solution was first posed in 1841. So you might be thinking to yourself, there weren't a lot of spacecraft flying around in 1841. The thing is, P and P, if you think about it for a little bit, is a surveying problem. And there was a lot of surveying going on in 1841. So if you were working as a surveyor and you had the line of sight direction to something that you got with a theodolite or some method of taking line of sight directions, and you've got multiple line of sight directions to points where you know how big that building is in the distance, you just need to compute your relative pose to it, that sort of thing. That's basically this. So it's the same problem. And so the way Gruner or Grunert first posed the problem was this. Let's say you've got a reference system over here. Maybe this is your X direction, this is your Y direction, this is your Z direction. And let's say that there's 3 points, and I'm going to draw them as being members of a right triangle, and that's completely arbitrary. That's just the way that I like to draw it. But there's 3 points in space. Okay. And let's say that each of those has some position, which we're going to call P1, P2, and P3. And really, I should be drawing vectors from the center to each of these points, but the diagram is going to get too busy if I do that. Then let's say that there's an observer out here somewhere, and that's you. You're the observer. And you measure a line of sight direction to P1, which we will call U1. Oh, sorry, that's P2. Whoops, there's U2. Here is U1. And then here, let's try that a little harder. Here, good enough, is U3. And now what we've really built here is a pyramid. This is a tetrahedron, right? Imagine that this triangle is the base of the tetrahedron, and then this point is like coming out of the page at you. You've got this 3-dimensional shape with side lengths A, B, C, S1, S2, and S3. Hopefully you see that this diagram is busy enough before I start drawing the arrows from the origin to these points. So in this case, it's clear that if we know P1, P2, and P3 in the world frame, then we know A, B, and C. And if we're measuring U1, U2, and U3, hopefully we can find S1, S2, and S3. That is the problem that Gruner posed in 1841. So to formalize that, given world points Pi, where I is 1, 2, and 3. So we're looking at the P3P problem right now. And line of sight vectors in the camera frame. I don't know that cameras existed in 1841. I feel like I should know the answer to that, but certainly not digital cameras. In this case, it could be a theodolite or some other sighting tool, right? And again, I is 1, 2, 3. And we are back to the hat, meaning that it's a unit vector. Yeah. We seek, whole shape is a tetrahedron. Tetrahedron side lengths. S1, I'll call this SI, where I is 1, 2, and 3. That's what we're after. That's the math problem. So the position of the world points in the camera frame is unknown. The position of the world points in the world frame is known, right? So really the unknowns are S1, S2, and S3. Now we should say here, side lengths are frame independent. That's nice to know. So what we can do right out of the gate is A is just the norm of P2 minus P3. You just think about that. The P2 minus P3 is now the vector from P2 to P3. Right? B is P3 minus P1, the norm of that. And then C is P1 minus P2, the norm of that. And we can also define some angles. And I want to go back and draw them on the diagram, but the diagram is busy enough. So you can imagine that alpha is the angle that is opposite of side A, right? So the cosine of alpha is U2 dotted with U3. Similarly, the cosine of beta is U1 dotted with U3. And the cosine of gamma, so beta is opposite B, gamma is opposite C, is U1 dotted with U2. All right. And so those are our three angles, and these are our three sides. So this is starting to look more and more like a high school math problem. And actually, we're going to solve this with high school math techniques. This is going to be a system of equations that we solve using change of variables and elimination, which is all stuff we learned in high school math. And so this is what we're starting with then. Oh, and we get to use our trusty old friend, which has been with us the entire time, but we haven't actually used it yet this semester. We begin by setting up the law of cosines 3 times. So we get a system of equations. So S2 squared plus S3 squared minus 2 S2 S3 cosine of alpha is equal to A squared. Similarly, S1 squared plus S3 squared minus 2 S1 S3 cosine of beta, that's B squared. And then we have S1 squared plus S2 squared minus 2 S1 S2 cosine of gamma is C squared. And this gives us a case of 3 equations and 3 unknowns, where there's 3 unknowns are S1, S2, and S3. All right, pause for questions. So far, so good. We're just setting up the problem. We know A, B, and C. We know alpha, beta, gamma. We can set up the law of cosines 3 times. And ultimately, we can try to solve for those 3 side lengths. So the next technique is going to be a change of variables. So we're going to say that S2 is defined to be S1 scaled by some unknown U, and S3 is defined to be S1 scaled by some unknown V. So there is no S2 anymore. There is no S3 anymore. It's just S1, U, and V. Okay. So how does that make things simpler? Well, now the first equation looks like S1 squared U squared plus V squared minus 2UV cosine of alpha is A squared. The second equation looks like S1 squared 1 plus V squared minus 2V cosine of beta equal to B squared. And the third equation looks like S1 squared U squared plus 1 minus 2U cosine gamma is equal to C squared. Or we can say that S1 squared is equal to A squared over U squared plus V squared minus 2UV cosine of alpha, but it's also B squared over 1 plus V squared minus 2V cosine of beta, and it's also C squared over U squared plus 1 minus 2U cosine of gamma. So all we did was just take those 3 equations, set it up as kind of a quadruple equals type equation here. And so after some algebra, and I'm skipping many steps because I'd like to get us out of here before midnight, after some algebra, we can solve for u in terms of v. And we can say, get ready for a big one here. U is equal to -1 plus a squared minus c squared over b squared v squared minus 2 a squared minus c squared over b squared cosine of beta v plus 1 plus a squared minus c squared over b squared. And then all of this is the numerator. And the denominator is 2, and then in parentheses, cosine of gamma minus v cosine of alpha. And if you'd like to work this out, that is left as an exercise to the reader. But what we have now, after just some tedious algebra, but something that you could imagine doing if you were being subjected to a punishment, then we ultimately get u in terms of v. So what we would then do is plug it back into the other equation. So we've got now, a case of 3 equations, 3 unknowns. We've removed S1, and now we have u in terms of v, so we plug that equation back in. And what we're building towards is a polynomial where the only unknown is v. So we're using, again, still high school math tricks, but further substitution leads us to a 4th order polynomial in v, which looks like this. A4 v to the 4th plus A3 v cubed plus A2 v squared plus A1 v plus A naught is 0. Okay, so hopefully you believe, even if we haven't gone through all the steps so far, that through various methods of substitution and elimination, we can go from 3 equations, 3 unknowns, down to 1 equation, 1 unknown. The only unknown is v, and it's going to be a polynomial. The problem is the polynomial is going to be ugly, and I mean, like, get ready for an uphill battle. Okay, here we go. A4 is equal to, oh, sorry, before we do that, d is defined as a squared minus c squared over b squared, because that's going to come up a lot. A4 is d minus 1 squared minus 4 c squared over b squared cosine squared of alpha. A3 is 4 d 1 minus d cosine of beta minus 1 minus a squared plus c squared over b squared cosine of alpha cosine of gamma plus 2 c squared over b squared cosine squared alpha cosine beta. All right, A2 is the worst one. Buckle up. A2 is 2 d squared minus 1 plus 2d squared cosine squared beta plus 2 b squared minus c squared over b squared cosine squared alpha minus 4 a squared plus c squared over b squared cosine alpha cosine beta cosine gamma plus 2 b squared minus a squared over b squared cosine squared gamma. And I can't believe I fit that all on one line. All right. It's not fun for you. It's not fun for me. My hand's cramping. Let's go. All right. 4 is negative d, and then in parentheses, 1 plus d cosine of beta plus 2 a squared over b squared cosine squared gamma cosine beta minus, in parentheses, 1 minus a squared plus c squared over b squared cosine alpha cosine gamma. And final push, a naught is 1 plus a squared minus c squared over b squared squared minus 4 a squared over b squared cosine squared gamma. All right, that was the big push. So give your hand a rest. Let it stop cramping. It's ugly. It's really, really ugly. But what do we have here? We have 5 numbers, A0, A1, A2, A3, A4, which we can compute using the magic of computers, that are entirely based on things that we know. A, B, C, D, which is a function of A, B, and C, alpha, beta, and gamma. That's it. So we can do it. So you can code this up in MATLAB once and then never have to do it again. And now you've got A0, A1, A2, A3, A4. Why do we care about that? Let's zoom back out again. Because if we can compute A0, A1, A2, A3, A4, we can solve this fourth order polynomial. We can find V, we can go back, we can find U, we can go back, we can find S1, we can find S2, we can find S3, and we're done, right? But here's the rub. Everything that we just did gets us a fourth order polynomial. What happens when you solve a fourth order polynomial? You don't get one answer, you get 4 answers. And so our work is not quite done yet, although we should be proud of ourselves for writing as much as we did. This monstrous equation will have up to 4 positive real roots, although it's generally only 2. So what I recommend is just guess and check. You've got 2 solutions. Let's take one, solve the whole dang math problem, and then check and see if our pose actually makes any sense. And then if it does, we're done. And if it doesn't, we go back and check the other one, right? So that's my method, is kind of guess and check. So what we could do then is say, for each candidate solution of V, find U using the equation that we have above, and then find S1, S2, and S3, and then compute pose and check. So that compute and check pose is going to be maybe raising some questions. And this is one of the questions that I've actually already gotten. Let's say for a minute that we know S1, S2, and S3. All right, so let's scroll back to our original problem. Let's say we fully understand this tetrahedron. We know S1, we know S2, we know S3. We know A, B, and C. We know these angles. That's not what Paul asked for. Paul asked for the position of this point, the observer, with respect to some global reference frame, and the orientation of the observer with respect to some global reference frame. That is a vector R and an attitude transformation matrix T. So S1, S2, and S3 are not a vector and a matrix. So we've got more work to do. So let's keep pushing. We've got another little sub-problem here. Let's say we know S1, S2, and S3. How to find, and I'm going to write this as the position in the moon-centered, moon-fixed frame, and the attitude transformation matrix from the moon-centered, moon-fixed frame to the camera frame. That's what we're after. And I should make a note that we now depart from Gruner's work, or Gruner. This is our own thing. So here's what I would conjecture. The point I expressed in the MCMF frame. So this is the ith point, the ith crater, is the position of the spacecraft, also in the moon-centered, moon-fixed frame, plus the vector from the spacecraft to the crater point, scaled by the distance s, and taken from the camera frame and put into the MCMF frame. Because U is naturally in the camera frame. So this right here, SIUI, is the relative position in the camera frame. All right. Hopefully that makes sense. Hopefully we agree with this statement so far. So really we're just saying position of the spacecraft plus the relative position is the position of the crater. Now what's neat about this is if you subtract them and we say, okay, P2 minus P1 is then equal to R plus, I'm going to abbreviate this as T for now because I'm getting lazy, S2U2 minus R minus TS1 U1. R minus R cancels out. And so what we get is P2 minus P1 is equal to T S2U2 minus S1U1. Okay. And again, this is the T from the camera frame to the MCMF or the world frame. Then what we can do is normalize both sides. And you might be thinking, why in the world are we going down this rabbit hole? Well, bear with me. What I'm saying is the vector from the first crater to the second crater in the world frame and the vector from the first crater to the second crater in the camera frame, I might have just said freighter, I meant to say crater. The relative positions of the craters, whether or not we scale them and normalize them, although it would be nice if we normalize them for this problem, it's the same vector, right? The vector from P1 to P2 in the world frame and in the camera frame is the same vector. There's just some unknown attitude relating them, but it's the same vector. And if we did this 3 times, then actually we come back to a very familiar math problem that we already know how to solve. So I'm going to say if you take P2 minus P1, I'm going to call that E12 MCMF. And if we take P3 minus P2, I'm going to call that E23 MCMF. And if we take P1 minus P3 and normalize that, we've got E31 MCMF. Similarly, if we take S2U2 minus S1U1 and then normalize it, that's going to be called E12 CAM. S3U3 minus S2U2, that is E23 CAM. And S1U1 minus S3U3 is E31 CAM. All right. Keep bearing with me. Again, these are just unit vectors, and it's the same unit vector, E12, E23, E31, just in 2 different frames. Now we're going to stack these together, and I'm going to say that E is E12 MCMF, E23 MCMF, and E31 MCMF. And A is E12 in the camera frame, E23 in the camera frame, and E31 in the camera frame. And you might have already guessed where we're going with this. By using the relative positions, the normalized relative positions of the craters in the camera frame, we have built up Waba's problem. So now the attitude profile matrix is A, E transpose. We can do the singular value decomposition on B, which would give us U, S, V transpose. We can say that M is defined as being an identity matrix, with the exception that the bottom right element is the determinant of U times the determinant of V, and this forces our solution to be right-handed. And finally, T from the moon-centered, moon-fixed frame to the camera frame is U, M, V transpose. So that's how we find our relative attitude, is we take the normalized relative positions of the craters and we solve Waba's problem. And then if we just keep pushing for one more step, finally, the position in the moon-centered, moon-fixed frame of you, the observer, is just the ith point. You could pick which one you want, or you could compute this 3 times and average them, minus, this is now going from camera to MCMF, SI, UI. And all this is the vector that the equation that we started with up here, just rewritten where we're solving for position. So position drops out really easily. Attitude is a little bit more of a fight. Okay, now we're still not done, but boy, we are coming in for a landing. Like the engines are off, we're on the glide slope, we're basically done. Right? Where are we now? All we have done is come up with a candidate pose. Remember I said guess and check? All of this is the guess. Now we have a guess of our attitude and our position. We have a guess of our pose. So finally, I keep saying finally, and then there's more stuff, sorry. We now have a candidate pose solution for each candidate V. So what we would then do is choose the pose which minimizes the reprojection error of the 4th point, or if there's more than 4 points, even better, but we'll focus on the 4th point for now. So let's go back to that equation. What do I mean by reprojection error? What I mean is we can compute where the crater 4, 5, 6, however many other craters you have, we can compute where they should be in the image, assuming our pose is correct. And then you can just take the angle between where it should be and where it is. And that's basically it. So if we write this equation again, PI is the spacecraft position plus T from camera to MCMF, SI, UI. Well, then if we rework this, we can say T from MCMF to camera of PI minus R, and then normalize that whole thing. That's UI. So this is how we would compute UI expected. So we're going to call this UI expected. Okay. And so then our error, which we are trying to minimize, our cost function, is the sum of the 4th through the nth crater, however many craters you have. 4 is plenty, but if you have more, that's fine. Of the arc cosine of UI expected transposed UI measured, what you actually see in the image, squared. So it's the sum of the squared angle errors between the actual line of sight directions to the craters and the expected line of sight direction to the craters if your pose was correct. And what you're going to find is that one of your errors should be very, very small, and the other error should be very, very large, because these aren't two similar pose solutions. They're actually going to be rather different pose solutions that come from an ambiguity. If you only have 3 points, you're kind of left with this ambiguity of different solutions. The 4th point allows you to nail it down and go, no, that's definitely the right solution. So I'm going to just quickly summarize this entire procedure in a flow chart, but you are welcome to key in your mic and interrupt with a question if something doesn't make sense. Otherwise, we are basically done. So the whole PNP procedure is compute A, B, C, alpha, beta, gamma. Then compute A0 to A5. Then solve fourth order polynomial for up to 4 candidate V's. For each candidate solution, compute U, S1, S2, S3. Solve for T and R, attitude transformation matrix and position vector. So that's your pose. And then predict line of sight to, I'm just going to say points 4 and above. So if you have 6 or 7, that's totally fine. 4 is the minimum. Finally, we keep the candidate solution that minimizes the sum of the squared reprojection error. I have good news. This is it. We're done learning navigation. That's everything. There's no other stuff. We're all done. That was a lot. This was a longer lecture than I would normally do. Apologies for that, but I wanted to make sure that everybody is well suited for homework 7 if you decide to tackle homework 7. Any questions on the PNP problem or just more generally solutions to crater-based navigation? Otherwise, I kind of want to let you go because like we're later than usual. All right, cool. Going once, going twice. Excellent. Well, I'm going to stop the recording, but stick around for a minute. Don't go just yet. But goodbye to everybody who's listening to the recording. Thanks for joining us.